If you're building software, you definitely know that feeling, right? That little rush when your code finally runs without an error.
Oh, yeah.
But the real jump, I think, the thing that turns you from just a coder into someone who builds, reliable systems, that happens when you really get automated testing.
That's so true. It's not just a safety net. It's really the secret weapon for code that you can actually maintain.
And that's exactly what we're doing today.
Hmm.
A full deep dive. We've got a great set of notes here covering everything from the big picture philosophy of test-driven development,
Right, the why.
all the way down to the nitty-gritty of Python tools like Unittest and Pytest. Our mission today is to give you the structure, the strategy you need to get past that brittle code phase.
Exactly. And start building systems that you can actually trust.
Okay, so let's dive right in with the big question.
Sure.
Why is testing now mandatory,
Yeah.
especially for Python developers? Why can't we just, trust our own logic?
Well, the why is really baked into the way Python works, especially when you compare it to, say, Java or C++ Wheat.
Right.
Those languages are what we call statically typed. So they do a ton of checking when the code is compiled.
Before it even run.
Before it even runs. The compiler is like your first line of defense. It catches all these basic errors like, you gave me a string, but I expected a number.
So you get this sort of built-in safety check that just wipes out a whole class of bugs from the start.
Precisely. But Python is dynamic. It waits until runtime to check those types.
So the error only shows up when the code is actually running.
And maybe only when a very specific, obscure part of the code gets hit. That's why testing is so much more critical in Python. Your test suite, it basically is your compiler check. It's how you find the bugs before your users do.
That completely reframes it. It's not just a quality step at the end. It's part of the core process of guaranteeing it even works. Which brings us to this quote in our notes from Kent Beck that I found really provocative. He said, "Software features that can't be demonstrated by automated tests simply don't exist."
And that's the philosophy right there. You have to internalize that. I mean, if you can't prove automatically that your code does what you think it does, how can you possibly rely on it?
So it's about more than just finding bugs.
Oh, way more. The sources lay out 4 main goals, and only one is about finding bugs. First, obviously, is to make sure the code works the way you, the developer, intend.
Sure.
Second, and this is where it really pays off, is preventing regressions. We've all been there. You fix a tiny bug over here.
And suddenly the login page is broken.
Exactly. A good test suite is that net that catches it. It tells you, hey, your change just broke something completely unrelated.
So it protects past work. What about the human side of things?
That's number 3. Testing confirms you actually understood the requirements correctly. It's so easy to misread a spec. But when you have to write a test, you are forced to define in concrete code what correct actually looks like.
Okay, and the fourth one seems to be about the future.
Absolutely. The 4th goal is to ensure your code has a maintainable, clean interface. Think about it. If a piece of code is really hard to write a test for,
It's probably hard to use in general.
it's probably too complex, too tangled up with other things. A difficult-to-test function is a huge red flag for future you or for the next developer who has to touch it.
All right, so once we buy into the why, we had to get to the how. And our notes have this great list of, they call them core mantras.
These are the rules to live by. The big one is test early, test often, test automatically. If you find yourself doing manual steps, copying and pasting data, you've already lost the battle.
Paired with that is my favorite. Coding ain't done till all the tests run.
I love that one too. It reframes the whole definition of done. It's not done when it works on your machine. It's done when the tests pass.
But there's a really important distinction here in the notes. It's not just about running every line of code.
No, absolutely not. That's a common trap. You need to focus on test state coverage, not just code coverage. It isn't enough to just execute a line of code.
You have to check what happened after.
Did the database value actually change? Did the function return the object you expected? You have to assert that the state of the world is what you wanted it to be.
And there's a tool for that, right? The coverage tool.
Yep, coverage. It's a simple idea, but it's so powerful. It runs with your tests and tells you exactly which lines of your source code were executed and which weren't. It gives you a percentage.
So you can see the gaps.
Exactly. But it's just a starting point. 100% coverage doesn't mean your code is perfect. It just means every line was touched. You still need the assertions to check the state.
Okay, this brings us to TDD, test-driven development. The notes argue this is less about testing and more about fundamentally changing how you design things.
It completely flips the script. The mantra is simple. Write tests first
Before the code.
before a single line of application code. And there is a critical warning here from the sources. Tests you plan to write later will never be written.
Haha, that feels a little too real.
It's true. Once a feature works and the pressure's on for the next one, the motivation to go back and write tests for the old thing just evaporates.
So TDD is a discipline tool.
It's two things. One, yes, it guarantees the tests get written. But
Yeah.
two, and this is the really big idea, it forces you to think about how your code will be used before you even write it.
Give me an analogy for that.
Okay, think about building like flat pack furniture. If you write the instructions after you've built the thing, they're probably going to be a mess. You'll forget steps.
Yeah, they always are.
Right. But if you're forced to write the instructions, the tests first, you immediately see where the design is clunky. You'd realize, oh, this screw doesn't fit here, or this interface is way too confusing.
So by defining the expectation first, you design a better product.
You're forced to design a cleaner, simpler, more usable interface. It also helps you break a big problem down into tiny, testable puzzles that you solve one by one.
That really clarifies the mindset shift. So we've got the philosophy down. Now let's look at the anatomy of an actual test. There's a standard pattern here.
There is. It's called the AAA pattern. Arrange, act, assert. It's so useful because it keeps your tests clean and easy to understand. It separates the setup from the action from the check at the end.
Okay, so walk us through those three plus the forgotten fourth step.
Right. First is arrange. This is your setup. You're lining up the dominoes. You create any objects you need, set up database records, you generate your specific input data.
So you create a predictable starting point.
A controlled environment. Then number 2 is act. This is the one thing you are testing. A single function call, a single method, just one state-changing action.
Only one.
Only one per test. Third is assert. This is the check. Did you get the return value you expected? Did the object's state change in the right way? And fourth, the one people forget, is cleanup.
Right.
You have to tear down whatever you built, close database connections, delete temp files. You have to make sure your test doesn't leave a mess that could affect the next test that runs.
The source material used a really simple, almost funny example for this from the Gherkin language about making tea.
Yeah, that's a great one because it shows how universal the pattern is.
So it's given a kettle on the stove and at tea, the burner is off.
That's your arrange, the controlled setup.
When we flip the lid on the kettle,
The act, the single action.
then we see steam escaping.
And that's your assert. You're checking the result against your expectation. It's that simple.
So once we get that basic unit test structure, we could zoom out to the bigger picture, the testing pyramid.
Right. And the pyramid structure is important because it tells you where to focus your effort. The foundation, the biggest part, the place you get the most value, is unit testing.
The small, isolated tests.
Exactly. They're fast, they're cheap to write, and they prove that your individual components, a single function, a single class work in isolation. If all your little bricks are solid, you'll have way fewer surprises when you build the wall.
Okay, so the foundation is strong. What's the next level up?
Next up is integration testing. This is where you check that the components work together. Does your code actually talk to the database correctly? Does your API client handle the data from the server?
And if that fails?
It usually means you defined an interface wrong or you missed a weird edge case in your unit tests.
Okay, so the parts work and the parts connect. But then there's a really big question. Are we even building the right thing?
And that brings us to the third level. Validation and verification. That's a crucial point. A bug-free system that solves the wrong problem is completely useless. So verification is, are we building the system right, according to the spec? And validation is, are we building the right system? Does it actually meet the user's need? You have to check that with the actual user early and often.
And finally, at the very top of the pyramid, once we know it's the right system and it's built correctly, can it handle the real world?
That's performance testing. Does it scale? Can it handle 10,000 users at once? What's the transaction per second limit? A system that works perfectly for one user but collapses under real-world load is still a failure.
Okay, this brings us to the really practical challenge, the one that gets everybody. How do you choose what data to test with? If a field takes a number from 1 to 1,000, you can't test every number.
No, you can't. That's exhaustive testing, and it's impossible and a waste of time. So we use smart strategies. The first one is called equivalence partitioning.
Okay, break that down for us.
The idea is that if your code works for one value in a valid range, it probably works for all the values in that range. So you just pick one representative. For that 1 to 1,000 example.
You test like 500.
Exactly. You test one valid number, like 500. Then you test one invalid number that's too small, like 0 or -5. And then one invalid number that's too big, like 1001. With just 3 tests, you've covered the general behavior for all possible inputs.
But the bugs, they always seem to cluster right at the edges, don't they?
They absolutely do. And that's why we have the second technique, which you use right alongside the first one. It's called boundary value analysis.
Okay.
Here, you focus specifically on those edges where the logic is most likely to break. So for our 1 to 1,000 range, you would test 6 specific points.
Dex.
You test the exact boundaries, 1 and 1,000. You test the numbers just below the boundaries, 0 and 999. And you test the numbers just above the boundaries, 2 and 1,001.
I
So
see.
you combine those 2 techniques, and suddenly you're getting massive test coverage with, maybe 9 or 10 powerful test cases instead of 1,000 useless ones.
Let's make this concrete. The source material has a great case study, building an average function using TDD.
Right, and the requirements are really specific. It takes a list of integers. That list can be empty, and it might have none values mixed in for, like, missing data.
Okay, so with TDD, the very first thing we do isn't writing the for loop, it's writing the test for the nastiest case.
Exactly. This is TDD in action. What's the worst thing that can happen? An empty list or a list with only knowns? In both cases, you'd be dividing by 0.
So you write a test that expects a division by 0 error.
Precisely. You write a test that only passes if that specific error is thrown. If it doesn't get that error, the test fails. That one test forces you from the very beginning to handle your input correctly.
And there's a neat little implementation hint in the notes for that.
There is. You don't have to write a loop to pull up the knowns. You can just use the built-in filter, known your list function, and that's a really clean way to do it. But you'd only think to build that filtering logic because your tests for an empty list and a list with only knowns forced you to.
Okay, so we know how to think about testing, how to design the cases. What are the actual tools in Python we use to do this?
You'll run into 2 main players. First is the one that's built right in, the Unittest library. It's the standard object-oriented way to do it.
And what's the syntax for that? What do you have to do?
You have to make a class for your tests, and it has to inherit from test case. And then critically, every single one of your test methods has to start with the prefix test. That's how the test runner finds them.
And it has those setup and cleanup methods built in.
Yep. They're called setup and teardown. And they run before and after every single test method, which guarantees a clean slate each time.
Okay. And the other big one, the one everyone talks about, is Pytest.
Right. Pytest is an external library, but it's incredibly popular for a reason. And it can actually run tests that you wrote using the Unittest style, so they work together.
What's its main selling point?
Automation and discovery. It just finds your tests. It looks for files named testsomething.py, classes named testsomething, and methods named testsomething. You write less boilerplate.
So it just handles all the organization for you.
It does. It'll scan entire folders and subfolders. But its real killer feature is something called fixtures. Think of them as setup and teardown on steroids. They let you define really complex, reusable test data, like a whole fake database connection or a mock user object, and then inject it directly into any test that needs it just by naming it as an argument. It's incredibly powerful.
Wow. Okay. This has been a really complete tour of the whole testing world. To sum it all up for you, the listener, our big takeaway is this. Automated testing is not optional, especially in Python. Test-driven development is really a design practice that happens to produce tests. It forces you to write better, cleaner code.
Absolutely.
And finally, use those strategies, boundary value analysis, equivalence partitioning, to test smart, not just test more.
And that leaves us with a final challenge for you because, listening is one thing, but doing is where you really learn. Our sources mention these classic programming puzzles, things like the dog and gopher problem or Morse code palindromes. They're problems where finding all the weird edge cases is really half the work.
So the challenge is?
Go find one of those problems, but don't just solve it. Use Unittest or Pytest. Write the test first, use the AAA pattern, think about all the boundary conditions we talked about, prove your solution works for every case you can think of. Because that active application, that's the only way to go from knowing about testing to being a developer who truly tests.